Hello everyone! So today here in Advanced Engineering Mathematics for Civil Engineers, we are now going to discuss the second part of Laplace transform. So for this lesson, students must be able to discuss and apply the properties and theorems of Laplace transform. So that is linearity of Laplace transform, first shifting theorem, S-differentiation theorem or derivative of transform, and integral of transform. So let us start our discussion. Okay, so these are the Laplace transform properties or theorems that we're going to discuss all throughout this topic. No, so the first one is linearity of Laplace transform. The second one is first shifting theorem. The next one is S-differentiation theorem or derivative of transform, and then integral of transform, Laplace transform of non-integer powers of t, Laplace transform of integrals, Laplace transform of piecewise functions, Laplace transform of unit step functions, and lastly, second shifting theorem. Okay, so it is very important, no, that we memorize the Laplace transform of some elementary function. So be sure to memorize that the Laplace transform of 1 is 1 over s, t is 1 over s squared, and then t raised to n, that will be n factorial over s raised to n plus 1, and then e raised to at, its Laplace transform is 1 over s minus a, cosine wt, s over s squared plus w squared, and then sine wt, its Laplace transform is w over s squared plus w squared. For hyperbolic cosine wt, that will be s over s squared minus w squared. And lastly, for hyperbolic sine wt, its Laplace transform is w over s squared minus w squared. So we are going to use all this established Laplace transform, no, for some elementary functions t, no. Okay. Okay, so the first property or theorem that we're going to discuss is linearity of Laplace transform. So linearity of Laplace transform has two propositions. So the first one is the Laplace transform of a sum or difference of functions, no, will just be equal to the Laplace transform individually of the functions. Okay, so we will just distribute the Laplace transform sign here, no? So the Laplace transform of f of t plus or minus Laplace transform of g of t, it will just be equivalent to this. Okay, and the second one is the Laplace transform of k times f of t, wherein k here is a constant. So if it is a constant, we can just take that constant out, no, of from the sign or symbol Laplace sign, no. So we can just take that out, no. So if there are cases, okay, that we are going to solve for Laplace transform of a product. Okay, so that product, no, if that product, the component of that product is not just a constant, no, so if it's just a constant, this is actually a product, no, product of a constant and of f of t. So if this is a constant, we can just take that out, no. But if it's a product of wherein the components of that product is not constant, okay, so we cannot use linearity of Laplace transform directly to that. Okay, we cannot do that. So we have to transform that product, okay, that product into its equivalent sum or difference. Okay, so there are basic fundamentals, math fundamentals that we can use, no, formulas that we can use to convert wherein it shows the equivalent of, let's say, from product to its equivalent sum or difference, no. So we will show that in our succeeding slide. Okay, and also we will also use, no, some Laplace transform properties and theorems, which will be discussed in the succeeding slides nga, no. So let's proceed. To recall here some fundamentals of math that we can use, no, for linearity of Laplace transform. So we can use this, no. So this is trigonometric identity, no, from product to sum or difference. So as we can see here, these are product of trigonometric functions, sine A, sine B, sine A, cosine B, cosine A, cosine B. So we cannot solve directly its Laplace transform. Let's say Laplace transform of sine A and sine B. No, we cannot apply linearity for that, okay? But we can apply linearity if we are going to convert this sine A, sine B into its equivalent sum or difference, which is this one. Okay, and from here, no, we can apply Laplace linearity of Laplace transform. And also for power, no, to sum or difference, let's say sine squared u, no. So of course, the Laplace transform of sine squared u, we cannot do that. We just get the Laplace transform of sine u and then square it, no? That's illegal, no? So we cannot do that. So that's a wrong answer if you do that, no? So to get the Laplace transform of sine squared u, we have to convert it into its equivalent sum or difference. So its equivalent sum or difference is this one, no? Same here for cosine 2u and 2 sine u cosine u. Okay, so these are the equivalent sum or difference. Okay, so lastly, no, for hyperbolic functions, okay, so we have to convert hyperbolic functions to sum or difference of exponential functions, no? So in this case, let's say a hyperbolic cosine of x, we can actually directly have it from the table, no, of established Laplace transform of some elementary functions, okay? But what if the given is hyperbolic cosine x tapos naka-squared? Okay? Cos squared x, let's say. No? So, we cannot do that. We just solve for the Laplace transform of hyperbolic cosine x and then we square it. No? So, that's not proper. No? That's a wrong answer. Okay? So, for that, for those cases, no, we have to convert, no, that hyperbolic cosine, okay, into its equivalent sum or difference of exponential functions, which are these equivalents, no. So also, no, if you're going to convert cos x to exponential functions and get its Laplace transform, no, it will actually be equivalent, okay, to the table that we have, okay, in Laplace transform for some for ano, no, the established Laplace transform for cos x or hyperbolic cosine x. So it will be the same. Okay. Okay, so let's start solving this, no? So find f of s if f of t is equal to t plus 2. Okay, so we are going to transform this given f of t or function of t, which is equal to t plus 2, to its Laplace transform. Okay, so we are going to solve f of s. To solve this, okay, so f of s will just be equal to the Laplace transform of the given f of t. So the given f of t is t plus 2. Okay, so here, the Laplace transform of t plus 2, okay, we are just going to apply the linearity of Laplace transform here since this is sum, no? Sum of two functions, t and 2. Okay, so we are just going to distribute the Laplace sign or symbol, no? So this will just be Laplace transform of t, and then since this is a plus here, so this will also be plus here, and then Laplace of 2. Okay, so here, we know already the Laplace transform of t, no, from the table, and that is just 1 over s squared, no? And the Laplace transform of 2, so here, the function here that has Laplace transform is 1. Okay, so meaning to say, we have to factor out 2 from 1, okay, or 1 from 2 rather. Okay, so what happens here will be 2 times 1. Okay, and then that's a product actually, right? 2 and 1. Okay, and the constant 2, okay, we can just factor that out. Okay, and factoring that out, what will just remain here is 1. And as we know, the Laplace transform of 1 is 1 over s. Okay, so solving this further, so the Laplace transform of t, that is just 1 over s squared, and then plus the Laplace so 2, no, and then the Laplace transform of 1, that will be 1 over s, so 2 times 1 over s, that will just be 2 over s. Okay, so we will make this a one fraction, so we will combine these two. Okay, so its common denominator will be s squared, so this will just be s squared divided by s squared times 1, so that will be 1, no? And then s squared divided by s, so that will be s times 2, so that will be plus 2s, no? So this will now be the answer for this, no? So we cannot simplify this further, so this is the simplest form for this. So this is already the Laplace transform of t plus 2. Okay, so let's proceed to number 2. So for number 2, find the Laplace transform of f of t is equal to e raised to negative 2t plus 1. Okay, so to solve this, we are going to solve for f of s. So that will just be equal to the Laplace transform of the given f of t, which is e raised to negative 2t plus 1. Okay, so here, as we know, we have here Laplace transform for exponential function, right? We have here e raised to 80. But the problem here is that the exponent here, okay, for this exponential function is a and t. It's just a times t. Okay, so in this case, this is not just a times t, no? So we have here plus 1. Okay, so here, no, we have to resolve first this e raised to negative 2t plus 1 in such a way that this one will be removed from ano, no, from negative 2t plus 1. Okay, so here we can use the law for exponents. No, so we can use law for exponent that we know that e raised to negative 2t plus 1, it's just equivalent to e raised to negative 2t times e. No, actually this is e raised to 1. Okay, e raised to 1, so that will just be e. No, this is equivalent, no, to this. Okay, so from here, as we know, this e is actually constant. Okay, there's a value for e here. So if you try to input that in your calculator, so that is I think 2.71828 and so on and so forth, no? So that's a constant. That value is a constant, no? So from here, this is product, no? Wherein this one of the component of that product is a constant. So we can apply linearity of Laplace transform here. The second proposition, we can use that. So we can just factor out this e, no, from the Laplace symbol here, no? So this will just become e, and then Laplace transform of e raised to negative 2t. So here, we already know the Laplace transform of this, no, from the table. So this is just e raised to 80, and its Laplace transform will just be 1 over s minus a, wherein this a is from this, no, from 80 here, no. So the a here will be the a here. Okay, so in this case, the a here, no, is negative 2. No, so if we apply our formula from the table, so this will just be e, and then the Laplace transform of e raised to negative 2t, that will just be 1 over s minus a, wherein our a is negative 2. So simplifying that further, that will just become 1 over s plus 2, and then times e, that will just become e over s plus 2. So this is now the simplest form for this. So this is already the answer for this. To sample problem number 3, find f of s if f of t is equal to cos or hyperbolic cosine squared to t. Okay, so in this case, okay, to solve this, no, so maybe you thought of this solution, no, that we know the Laplace transform of cos 2t, no, from the table. And if we solve that, we just square that answer, no? So this is the Laplace transform of cos 2t from the table. So we use this, okay? So this is s over s squared minus w squared. So we just apply that, and then we square it. Class, this is actually wrong. So this is a wrong solution, no? So this is a wrong answer, okay, if you do this, okay? So this is not linearity of Laplace transform, okay? So we cannot apply this, no? So the right solution for this, okay, so since our given here is cos squared 2t, no? So we know that we can transform cos 2t, okay, into its equivalent sum or difference of exponential function, right? So we can transform it that way. So that's our right solution. Okay, so we have to transform first this cos 2t squared, no, into its equivalent sum or difference of sum or difference of its exponential function, no. So this will be that, no, this is hyperbolic to sum or difference of its exponential function or equivalent, no? So cos x is actually e raised to x plus e raised to negative x over 2. So the x here will be the x also here. Okay, in the exponent, no? So if we have here cos 2t, no, so we can do this, no, cos 2t, and then we just square it, no. So cos 2t, our x here will be 2t. Okay, so we just substitute 2t to the exponent. So that will be e raised to 2t plus e raised to negative 2t over 2. And we will just square that, no? So since this is squared here. Okay, so from here, simplifying this, no, squaring this, no, so this will just be e raised to 4t plus e raised to negative 4t plus 2 over 4. So we can simplify that, no, so you can manually multiply e raised to 2t plus e raised to negative 2t times e raised to 2t plus e raised to negative 2t, no? So that is a square of that, no? Over 2 squared, which is 4. So this will be the result for that, no? If you simplify this. Okay, so from here, as you can see, f of t now is equal to e raised to 4t plus e raised to negative 4t plus 2 over 4. Okay, so we can actually use linearity of Laplace transform here already, since this is already a sum or difference, right? Okay, so from here, applying linearity of Laplace transform, okay, so we can factor out 1/4 here. Okay, we can factor that out since that is a constant. Okay, and then the Laplace transform of e raised to 4t plus e raised to negative 4t plus 2. Okay, so from here, we can distribute the Laplace symbol here, since this is already a sum, no? Okay, so this will become 1/4, and then Laplace transform of e raised to 4t plus Laplace transform of e raised to negative 4t, and then Laplace transform of 2. So as we know, this is already available from the table. We know the Laplace transform of e raised to 4t, Laplace transform of e raised to negative 4t, and the Laplace transform of 2, no? So we can directly solve for its Laplace transform. So for the Laplace transform of e raised to 4t from the table, so e raised to 80, our a here is 4. So that will just be 1 over s minus a, wherein a is 4. So that will be s minus 4. And then the Laplace transform of e raised to negative 4t, that will just be 1 over s minus a. Our a here is negative 4. So s minus negative 4, that will become s plus 4. And then we have here Laplace transform of 2. So that will just be Laplace transform of 1, which is 1 over s times 2. So that will be 2 over s. Okay, so simplifying this further, okay, we can combine these three, no? So we can solve for its um, uh, least common denominator, no? So that will be s minus 4 plus, times s plus 4 times s. Okay, so this will be s minus 4 times s plus 4 times s divided by s minus 4 times 1. So that will be s times s plus 4. And then s minus 4 times s plus 4 times s divided by s plus 4 times 1. So that will be plus s times s minus 4. And then s minus 4 times s plus 4 times s divided by s times 2. So that will just be 2 times s minus 4 times s plus 4. Okay, so simplifying this further, no? Okay, so we can combine s minus 4 times s plus 4. So that is just s squared minus 16. And then we also combine it here, no? Okay, so after that, we can simplify this further. If we distribute this, no, and this, so, no? Okay, so this will become s squared plus 4s plus s squared minus 4s plus 2 times s squared minus 32 over s times s squared minus 16. Okay, so from here, okay, so f of s now will become 1/4 times 4s squared minus 32. So we just combine like terms here. We combine all s squared here, and we combined all s here. So apparently s here are cancelled, no? Okay, and then we just combine the constant. So the only constant here is negative 32. So this will what will remain. Okay, so from here we can simplify this further. We can factor out 4 from 4s squared minus 32, right? So that we can cancel 1/4 here. Okay, so factoring out 4 here, so that this will become 4s times s squared minus 8, and then 4 will be cancelled. So the answer for this will become s squared minus 8 over s times s squared minus 16. So this will now be the answer for this. Okay, so, okay, let's proceed to another sample problem. Okay, for sample problem number 4, find f of s if f of t is equal to sine 2t times sine t. So as you can see here, the given f of t here is a product of sine 2t and sine t. No? So we cannot do in our solution that its Laplace transform, no, will just be the Laplace transform of sine 2t, and then we multiply it to the Laplace transform of sine t, which is this, no? So this is wrong. So this is a wrong solution. So this is not no linearity of Laplace transform. So we cannot do this. So this is a wrong answer. Okay, so for this, no, to solve this, okay, so since this is a product, no, of sine 2t and sine t, we have to transform this product sine 2t sine t into its equivalent sum or difference. Okay, so from our this, no, this is fundamental from trigonometry. Okay, so we have here a product of sine A and sine B, which we can apply for this. Okay, so this is equivalent to 1/2 of cosine A minus B minus 1/2 of cosine A plus B, wherein A here will be this, no, which is 2t, and then B here will be this B, so this will be T, no? Again, A is 2T and then B is T. So we will just substitute that here. Okay, so for our solution, we transform first the given f of t into its equivalent sum or difference. So this will be that, no? So this will become 1/2 cosine of 2t minus t minus 1/2 cosine 2t plus t. So we just follow this formula. We just substitute A and B here. Okay, so simplifying this, so this will become 1/2 of cosine t and then minus 1/2 of cosine 3t. Okay, so from here, we can now apply linearity of Laplace transform. So since this is already a difference. Okay, so applying Laplace transform here. So the Laplace transform of 1/2 cosine t minus 1/2 cosine 3t. So we just apply linearity of Laplace transform. We just distribute, okay, the Laplace symbol, no? So this will become 1/2 of Laplace transform of cosine t. So we already applied the second proposition. We factor out already the constant here, same here. So this will become minus 1/2 of Laplace transform of cosine 3t. So from the table, we can solve for the Laplace transform of cosine t. So from the table, cosine wt. So in this case, our wt here, or the w here, is 1. Okay, since this is cosine t, no? This is also equivalent to cosine 1t. So our w for this is 1. And then here, our w for this is 3. Okay, so we will use that here. This will be s over s squared plus w squared, wherein the w for this is 1. So 1 squared, w squared. So this is w squared, so that will be 1 squared. That will still be 1. Okay, minus, okay, cosine 3t, Laplace transform of cosine 3t. So the w is 3, so that will be s over s squared plus w squared. W is 3, so that will be 3 squared, so that will be 9. So we just factor out 1/2 here, no? Again. Okay, so here we are going to combine these two terms, okay, or function, no? So we are going to solve for its least common denominator, which is s squared plus 1 times s squared plus 9. Okay, so this will become s squared plus 1 times s squared plus 9 divided by s squared plus 1 times s. So that will just be s times s squared plus 9. And then s squared plus 1 times s squared plus 9 divided by s squared plus 9 times s. Okay, since negative here, that will be negative s times s squared plus 1. So simplifying this further, okay, so this will be distributed. So this will become s cubed plus 9s minus s cubed minus s over the same denominator. Okay, we can just let this as it is, no? So no need to distribute this further. Okay, this will do already. Okay, so here we will simplify the numerator. So we can combine like terms here. We can combine all s cubed. We can combine all s here. So this will become s cubed minus s cubed, so that will be cancelled. And then 9s minus s, so that will be 8s over the same denominator here. So we can actually cancel 2 here, okay? We can factor out 4 from 8s, so that will become 4 times 2, 2 rather, factor out 2. So that will become 2 times 4s, so we can cancel that 2, no? And this 1/2, no? Okay, so from that, no, so this will become 4s over s squared plus 1 times s squared plus 9. So this will already be the answer for this. Okay. Okay, so let's proceed now to the second theorem, which is the first shifting theory. Okay, so for this theorem, if f of t has the transform f of s, then e raised to 8t times f of t has a transform of f of s minus a. Thus, the Laplace transform of e raised to 8t times f of t, that will just be equal to the Laplace transform of f of t, okay, wherein s you will convert it into s minus a. Okay, so here, okay, so for our given f of t, okay, let's say the given f of t is this. So this is another f of t. So the general given here, okay, is, let's say, e raised to 8t times f of t. So this is our given f of t, let's say. Okay, so if the given is e raised to 80 and then it is multiplied by any function, okay, of course, we cannot use linearity of Laplace transform here because this is a product, no? So automatically, if the product, if one of the components of the product is e raised to 80, okay, for the given f of t, okay, so what we're going to do here, okay, to solve for its Laplace transform, we just solve for the Laplace transform of the function, okay, that is multiplied by e raised to 80, which is this f of t. Okay, so we just get the Laplace transform of this f of t. So this is any function, okay, that is combined with e raised to 80. Okay, so we just solve for its Laplace transform. So that Laplace transform, that will be in terms of frequency variable s, right? So that's the Laplace transform of that. So all those frequency variable s, we will convert them, okay, into s minus a. Where in this a, okay, we will get this a from the a in your e raised to 80. Okay, so can you get that? Okay, so that's just the condition for this, okay, to use first shifting theorem. Okay, your given should have a component in the product of e raised to 80. And then this f of t, this can be any function. Okay, and if that's the given, okay, you can just use this formula. You will just get the Laplace transform of the function that is combined with e raised to 80, which is this f of t, and then convert the variable s from the Laplace transform of this to s minus a. Where in a here, okay, we get this from here. Okay, so that's just as simple as that. Okay, so let's solve sample problem number 1 for this theorem. Okay, find f of s if f of t is equal to t times e raised to negative 2t. Okay, so apparently, if you're going to solve this, okay, so this is a product. Okay, if this is a product, we cannot apply linearity of Laplace transform here. We cannot do that. We just solve for the Laplace transform of t, and then we just multiply to the Laplace transform of e raised to negative 2t. So that's illegal. We cannot do that. That's a wrong answer. That's a wrong solution. Okay, so here, the right solution for this, okay, since we know, okay, that our given here is a product wherein one of the components of the product is e raised to negative 2t. Okay, so that's actually the condition, okay, for us to be able to use first shifting theorem. Okay, your given should have e raised to 80. Okay, for us to apply this, no? So since the given here has e raised to negative 2t, and then the f of t, therefore for this will be t. Okay, so applying first shifting theory here, we will just solve for the Laplace transform of f of t. So the f of t for this is t. And then what we're going to do is, if we already solve for the Laplace transform of t, so that will now become in terms of s, or frequency variable s. So we just have to replace s with s minus a. Okay, we're in a here. this will come from e raised to negative 2t. So our a here is negative 2. So that this will become s minus negative 2. Okay, so solving this, the Laplace transform of t from the table, that is 1 over s squared. And then we will just replace all variable s to by s plus 2. So this s will become s plus 2. So this will now become 1 over s plus 2 squared. No, so this will now be the answer for this. Okay, so this is just simple, right? Okay, so let's now solve sample problem number 2. Find f of s if f of t is equal to cos t times cosine 2t. Okay, so our given here is a product. Product of cos t and cosine 2t. Okay, so from linearity of Laplace transform, so we cannot use that here since this is a product. So our choice here is that we have to transform this in such a way that it will become sum or difference. Okay, so for this is cos t and cosine 2t. Of course, we cannot use a product of trigonometric, yung sine, cosine, okay, because that's just a product of trigonometric functions, sine and cosine. Okay, in this case, this is cos. Okay, so we cannot apply that. So our option here is that we can convert, no, we can transform cos t into its equivalent exponential function. Okay, sum or difference of exponential function, which is this. Okay, so we know that cos t, okay, if we convert that, that will just become e raised to t, okay, e raised to t plus e raised to negative t over 2. Okay, so that's the equivalent of cos t. Okay, and if it will be multiplied to cosine 2t, if we distribute this, okay, to cosine 2t, this will become the result. Okay, so this will be 1/2 t. Okay, again, that will be 1/2 e raised to t times cosine 2t. So this will be that, no? And then 1/2 times e raised to negative t times cosine 2t. So this will be the result. Okay, so from here, if you can see here, okay, we can apply linearity, okay, or, right, linearity of Laplace transform. Here, we can just distribute the Laplace transform for this and this, okay? So individually, okay, as we can see, okay, we can apply, no, let's say for this, for the Laplace transform of e raised to t cosine 2t, we can apply first shifting theorem here. Why? Because there's a e raised to t here. This is a product, yes, but there's e raised to t here. So we can apply first shifting theorem here. So our f of t here will be cosine 2t. Right? So same here. Since we have here e raised to negative t, so that's the requirement for us to be able to use first shifting theorem. So the f of t here, okay, will be cosine 2t. So applying that, no, first shifting theorem, so that will just become, we will just solve for the Laplace transform, okay, Laplace transform of f of t. So in this case, the f of t here is cosine 2t. So the Laplace transform of cosine 2t, that will become in terms of frequency variable s. So we will just replace all variable s, okay, by s minus a. So our a here for this term is 1t. So our a is 1. So this will be s minus a, s minus 1. And then for this, okay, so we have here, we will apply this. So this will just be the Laplace transform of f of t. So our f of t here is also cosine 2t. And then we will replace all variable s by s minus a. So our a here is negative 1, right? So that will be s minus negative 1. That will become s plus 1. So from here, we can now solve the Laplace transform. Okay, so the Laplace transform of cosine 2t from the table, okay, from the table, that will just be s over s squared plus w squared. So in this case, our w here is 2. So w squared, so that will be 2 squared, that will be 4. So this will become s over s squared plus 4. But we are going to replace all variables s by s minus 1. No? So same here. Okay, the Laplace transform of cosine 2t, that will also be the like here. So that will be s over s squared plus 4. We will just replace all the variables s by s plus 1. So replacing now all variables s, no, by s minus 1. So this s will become s minus 1, and then this s squared will become s minus 1 squared plus 4. So same here, s will become s plus 1, and then s squared will become s plus 1 squared plus 4. So simplifying this, so we can simplify this further. We can factor out 1/2. Okay, after factoring out 1/2, okay, we can combine these two terms, okay, by solving for its common denominator. Okay, but before that, we can simplify this further. S minus 1 squared plus 4, that is equivalent to s squared minus 2s plus 5. So we just expand s minus 1 squared, and then we added 4. No, same here, s plus 1 squared plus 4. We just expounded s plus 1 squared and then add 4. So that will become s squared plus 2s plus 5. Okay, so from here, we can have the common denominator for these two terms, no? So this will be s squared minus 2s plus 5 times s squared plus 2s plus 5. So this will become s squared minus 2s plus 5 times s squared plus 2s plus 5 divided by s squared minus 2s plus 5 times s minus 1. So that will become s minus 1 times s squared plus 2s plus 5. Also, s squared minus 2s plus 5 times s squared plus 2s plus 5 divided by s squared plus 2s plus 5 times s plus 1. So that will become plus s plus 1 times s squared minus 2s plus 5. So simplifying this further, okay, we just distribute this also and this, no? And then distributing them, so this will now be the result. And then combining like terms, we combine all s cubed, we combine all s squared, we combine all s, and we combine all the constants here. Okay, so this will now be the result. So this will become 2s cubed plus 6s over s squared minus 2s plus 5 times s squared plus 2s plus 5. Okay, so we can cancel this 1/2 by factoring out 2 from the numerator. So factoring out 2. So that will become 2 times s cubed plus 3s. Okay, so we can factor out, cancel out 2 and 1/2. So the answer will become s cubed plus 3s over s squared minus 2s plus 5 times s squared plus 2s plus 5. So this will now be the answer. Okay. Okay, so let's proceed now to the third theorem, which is S-differentiation theorem. Okay, so this is also called derivative of transform. So basically, we're going to use the your basic knowledge about derivatives. Okay, so if f of t has the transform f of s, then, okay, the Laplace transform of t raised to n times f of t is equal to negative 1 raised to n times the derivative with respect to s with order n of Laplace transform of f of t. Okay, so to simplify this, okay, so let's say our given f of t. Okay, our given f of t, okay, general given, okay, the general given f of t, it is a product. If it's a product and then one of the components of that product is t raised to n, and then if the another component is f of t, okay, let's say f of t is any function. Okay, so what we're going to do here, okay, we can apply this theorem. Okay, as long as the given has t raised to n. As long as the given is a product, okay, wherein one of the components is, let's say, t squared, t cubed, and then if it's combined with any function, let's say e raised to t, or another function, okay, trigonometric function, let's say. Okay, so what we can do here is just solve this using this formula. So this will be negative 1 raised to n, wherein n here, okay, is from the exponent of t. Okay, so if the exponent of t is just 1, so this will just be 1. If the exponent of t is 2, so this will be 2. Okay, and then we have here the derivative, okay, with respect to s with order n. So our order here will depend here. So the order, that means that's the number of times that you need to derive your this Laplace transform of f of t. So meaning to say, if this is just 1, if n is just 1, you will just have to derive, okay, this, okay, once. Okay, if it is 2, if it is t squared here, so the n is 2, so you have to derive, no, to perform derivatives twice for this, no, for the Laplace transform of f of t. Wherein f of t here, Okay, so it came from here. Okay, so f of t here is the function that is combined with t raised to n. Okay, so you just have to solve for its Laplace transform, and then after solving for this, for the Laplace transform of f of t, you're going to derive that, no? Depending on the number of order. If it's once, twice, thrice, okay, it depends. Okay, so that's the only condition here, okay, for you to be able to use this. Your given should be a product wherein one of the components of the product is t raised to n. Okay, so let's start solving. So let's solve sample problem number 1 here. Find f of s if f of t is equal to t times e raised to negative 2t. Okay, so for this given f of t, okay, so our given here, this is a product, okay, wherein one of the components is t. Okay, if one of the components is t raised to n, so this is basically t raised to 1. Okay, so we can apply S differentiation for this. Okay, so applying S differentiation, we will just apply this formula wherein our f of t for this will be e raised to negative 2t. So we will just use this formula, okay, negative 1 raised to n, wherein our n here, since this is t, so that will just be 1. And then 1, our n here, so that will be the order of the derivative. So that will just be 1. So we will just derive once the Laplace transform of f of t, wherein our f of t for this will be e raised to negative 2t. Okay, so let's start solving this using S differentiation. So we just substituted this here. Okay, negative 1, so 1, derivative of Laplace transform of e raised to negative 2t. So that is the given f of t for this, okay. So we will solve first for the Laplace transform of e raised to negative 2t. So from the table, we can solve that easily. So the Laplace transform, okay, of e raised to negative 2t, that will just be 1 over s minus a, wherein a is negative 2, so that will just be s minus negative 2, that will become s plus 2. So for this, negative 1 raised to 1 will just be negative 1, okay? And then we are going to derive now this 1 over s plus 2. So we will derive this with respect to s. So deriving this, no, we can apply quotient rule for derivative, but we can also just simplify this, no? We can rewrite 1 over s plus 2 as s plus 2 quantity raised to negative 1. Okay, so we can also do that, right? So this is also equivalent. This s plus 2 raised to negative 1, this is also equivalent to this 1 over s plus 2. So we can now derive this, no? So we can use power rule here. Okay, and at the same time, we will use chain rule for this, for differentiation. So deriving s plus 2 raised to negative 1, so that will just be applying power rule, that we will just bring down negative 1, so that will become negative 1. And then we will subtract negative 1 by 1, no? So that this will become negative 1 minus 1, which is negative 2. And then s plus 2. And then we will derive this function inside. So the derivative of s plus 2 will just be, what's the derivative of s? That is actually just 1 if we are going to derive this with respect to s. So the derivative of s is just 1, and then the derivative of 2 will just be 0. So this, basically, the derivative of s plus 2 is 1. So this will just be multiplied by 1. But we did not show it anymore here, no? So obviously, that will just become the same. Okay, so simplifying this, so this will become negative 1 times negative 1, so that will become positive, and then s plus 2 raised to negative 2, so we can rewrite it this way, so this will become 1 over s plus 2 squared. So this is also equivalent here. So this is now the answer for this. Okay. Okay, so the next one, for sample problem number 2, find f of s if f of t is equal to t squared times sine t. Okay, so again for this is a product. Okay, so we will apply S differentiation here, since our product, one of its components is t squared. So that's the only requirement for us to be able to use S differentiation. So our f of t, therefore, here will be sine t. Okay, so we will just substitute that. And our n here, if we apply our formula, our n will be 2. And then again, our f of t here will be sine t. So to solve this, we just substitute that. And then this will become negative 1 squared, and then derivative of Laplace of sine t with respect to s with order 2. So meaning to say, we will derive the Laplace transform of sine t twice. Okay, so let's first solve for the Laplace transform of sine t. So from the table, that will just be sin wt, its Laplace transform is w over s squared plus w squared. So in this case, our w here is 1. So that will just be w squared or 1 squared. So that will just be 1. So this will now be the Laplace transform of sin t. Okay, so we will derive this 1 over s squared plus 1 twice. Okay, so deriving this, okay, so we can rewrite 1 over s squared plus 1 this way. So this is s squared plus 1 raised to negative 1. But we can also use, we can also use quotient rule for differentiation for this. So we can also use that. Okay, so whichever way is more, convenient to you, so you can use that. Okay, so for this, we will we will solve it this way. Okay, so deriving deriving for the first time s squared plus 1 raised to negative 1. So applying power rule and chain rule for this. So this will just be negative 1. You just bring that down. And then negative 1 minus 1, that will be negative 2. And then we just solve for the derivative of s squared plus 1. So that will be 2s. Okay, chain rule. That's chain rule. Okay, so you recall that in your you recall your basic differentiation rules. Okay, so for this, we simplify this. Okay, so this will become negative 2s over s squared plus 1 squared. So we just bring down s squared plus 1 raised to negative 2. If we bring that down, that will become positive, the exponent. Okay, so this is just equivalent to this. Okay, so this is not finished yet. Okay, we have to derive this again for the second time. Okay, so we have to derive negative 2s over s squared plus 1 squared. So for this, we have no choice, okay, but to use quotient rule. Okay, so for our quotient rule, no, recalling that, that is just the derivative of u over v, that is just v du minus u dv over v squared, no, if you can recall that. So we will apply that here. Okay, so this will now become, so again, that is v du. So our v here is s squared plus 1 squared, and our u here is negative 2s. So v, and then derivative of u, v du, v times derivative of u. So the derivative of negative 2s is negative 2. Okay, minus v, our v is negative 2s, and then v du. So our, v du minus u dv rather. So our u here is negative 2s, u dv, and then derivative of v. So the derivative of v will just be 2, no, times s squared plus 1 times 2s. So chain rule, no, we use chain rule and power rule for that to derive v. Okay, so from that over v squared. So our v is s squared plus 1 squared. So we will square that further. Okay, s squared plus 1. So we will quantity square that. Okay, so from here, we will simplify this. Okay, so simplifying this, we just multiply it, no? Okay, so after multiplying it, we can distribute this further, I think. Oh, no, we can factor out s squared plus 1 from here. Okay, so factoring out s squared plus 1. So since we have here 2s squared plus 1 squared here, and then 8s squared plus 1. So this term both have s squared plus 1. So we can factor out, actually we can factor out 2s squared plus 1. Since 8, no, we can factor out 2 from that, no, from 8s squared, that will become 4s squared. So factoring out 2s squared plus 1, so that will become, so for this, no, 2s squared plus 1, for this will just become negative s squared plus 1. Okay, from here. And then 2 times s squared plus 1. Okay, so from here, so this will just become plus 4s squared. Okay, we just factor out 2 times s squared plus 1. Okay, so from here, this s squared plus 1 will just be cancelled. Okay, if you can see in the denominator, this is also s squared plus 1. So 1 from this s squared plus 1 to the fourth, 1 of its s squared plus 1 will be cancelled. So this will become s squared plus 1 cubed, no, the denominator. So this will become 2 times 3s squared minus 1 over s squared plus 1 cubed. So this will now become the answer for this. Okay, so we will now proceed to the next theorem, which is integral of transform. So if f of t has the transform f of s, then the Laplace transform of f of t over t will just be equal to the integral of f of u du, okay, from s to infinity, wherein f of u is Laplace transform of f of t expressed in u. Okay, so to simply put this, okay, so if we have a general given f of t, which is f of t over t, meaning to say this f of t is any function. So this is any function, and if it's divided by t, okay, we can use this theorem. Okay, let's say that our f of t here is, let's say, e raised to 80 over t. So if that's e raised to 80 over t, our f of t for that, okay, this f of t for that is e raised to 80. And we can just use this. Okay, that this f of u, okay, this is actually the Laplace transform of f of t, but this is expressed in u. So instead of expressing it in s, frequency variable s, we will express it in u. Okay, and we will integrate, no, this f of u with respect to u. Okay, and we will evaluate this from s to infinity. Okay, so that's just the condition for this. Our given should have over t, okay, or 1 over t, no, in the given general f of t. Okay, so let's try to solve some problems for this theorem. Okay, for sample problem number 1, find f of s if f of t is equal to 1 minus e raised to negative 2t over t. Okay, so there's actually a t here. Okay, so the denominator here is t. So we can actually apply the integral of transform. Okay, we can apply this. Okay, so our f of t for this is 1 minus e raised to negative 2t. Okay, so what we're going to do here is solve for the Laplace transform of f of t and then express s, no, frequency variable s in terms of u. So that will be the f of u. Okay, and we will just integrate that with respect to u from s to infinity. Okay, so let's start solving this. Okay, so again, um, we will use this formula since we know that we can apply this. Okay, so our f of t here will be 1 minus e raised to negative 2t. So we will solve for the Laplace transform of 1 minus e raised to negative 2t, and we will express its Laplace transform in terms of u. Okay, so solving for the Laplace transform of 1 minus e raised to negative 2t, we can apply linearity, okay, of Laplace transform for that. So that will just be, what the Laplace transform of 1, what will be the Laplace transform of 1? Okay, so that is actually 1 over s. But instead of using s, you will use u. So that will be 1 over u. And then the Laplace transform of e raised to negative 2t, so from the table, that will just be 1 over u plus 2. Okay, so instead of using s, again, instead of using s, we will use u here. Okay, and then this answer, 1 over u minus 1 over u plus t, okay, we will integrate this with respect to u. Okay, so how can we integrate 1 over u and 1 over u plus 2? So we can apply, okay, the integration yielding to logarithmic function that we learned from our integral calculus. So I believe that you still remember this. Okay, the derivative of du over u is equal to ln u plus c. Okay, so for this, we will not include plus c because this is definite, no? We have limits here, s to infinity. Okay, so the first one, the integral of 1 over u times du, so that will just be du over u, right? So that will just be ln u. And then the derivative, or integral rather, the integral of du over u plus 2, so we will also apply this, so that will just become ln of u plus 2. So applying this, okay, so again, the integral of 1 over u times du, that will just be ln u. Okay, minus. the integral of 1 over u plus 2 times du, that will just be ln of u plus 2. So we will evaluate this from s to infinity. So we will substitute infinity to all the values of u minus, and then we will substitute s to the value, to the variable, to all the variables u here. Okay, so substituting the upper and lower limit, so that will just become ln of infinity minus ln of infinity plus 2. Okay, minus, okay, we will now substitute s, ln of s minus ln of s plus 2. Okay, so simplifying this, okay, so as we know, ln of infinity, if we try to input that in our calculator, let's say ln of 9999999, so that is infinity. Okay, so that will go on and on. So ln of 99999999999. Okay, so there will be an answer for that actually. Okay, minus, okay, ln of u plus 2. Okay, ln of u plus 2, or infinity rather, ln of infinity plus 2. Now, what is infinity plus 2? Okay, if you add 2 to infinity, okay, would that infinity change? No, that will still be an infinity, right? If you add a number to infinity, that remains as infinity, right? So definitely this ln infinity plus 2 will just be ln of infinity as well. So ln of infinity minus ln of infinity, that will just be 0. Right? So that will become 0, and then we have here negative ln s minus ln s plus 2. So we just distribute the negative here. Okay, so this will become negative ln s plus ln s plus 2. So simplifying that further, okay, we can apply the law for logarithm here. Okay, that for sum, okay, or difference of two logarithmic function, okay, let's say ln s plus 2 minus ln s, so we can apply this rule for that, no? So we can use the quotient, okay, if we combine these two, no, this can become ln of s plus 2 over s. Okay, that is ano ha, ln of s plus 2 minus ln s, we can apply that we can rewrite that into, let's say, ln of x minus y. We can rewrite that as ln of x over y. Okay, that's the rule for that. So we will apply that here. So our f of s here is ln of s plus 2 over s. So this will now be the answer for this. Proceed now to number 2. Find f of s if f of t is equal to t raised to negative 1 times sine 2t minus sine 3t. Okay, so for our given, okay, this is actually a product of t raised to negative 1 and sine 2t minus sine 3t. So as we know, this t raised to negative 1, this is just equivalent to 1 over t. Right? So from here, no, we can apply integral of transform. So since t raised to negative 1, that is just equivalent to 1 over 2. So we can apply this. Okay, and the f of t for this will be sine 2t minus sine 3t. Okay, so we will just apply our formula here. Okay, so this will just become the integral of f of u, wherein f of u is the Laplace transform of f of t, which is sine 2t minus sine 3t, expressed in u. And then we integrate it with respect to u, and then we evaluate from s to infinity. Okay, so solving for the Laplace transform of sine 2t minus sine 3t, that will just be 2 over u squared plus 4. So from the table, no, so that will be the Laplace transform. So instead of using s, expressing it into s, we will express it into u. Okay, so also here for sine 3t, its Laplace transform will be 3 over u squared plus 9 expressed in u. Okay, so we will now integrate this, no, these terms. Okay, we will integrate 2 over u squared plus 4 du, and then integrate 3 over u squared plus 9 du. So what are we going to use to solve for its integral? So going back to your integral calculus, we will use this integration yielding to inverse trigonometric function. Okay, so we use this formula. Okay, so the integral of du over u squared plus a squared is just equal to 1 over a arctangent of u over a plus c. So in this case, we will no longer include plus c because this is a definite integral, okay, since we have here limits s to infinity. Okay, so we can apply this. Okay, for this, the integral of 2 over u squared plus 4 du, our a squared for this will be 4. Okay, therefore our a is 2. If a squared is equal to 4, our a is 2. Okay, also for this, we will apply also this formula. Okay, so our a here will be 3. Okay, since 9, that will be the a squared. So therefore, a is 3. Okay, so applying our formula, so that will just be, okay, for the first one, for the integral of this with respect to u, that will just be 1 over a. Our a here is 2, 1 over 2. And then we just, how, we just factor out 2 here, okay, since this is a constant. And then arctangent, okay, so this is just the same. Arctangent of u over a, our a is 2. Okay, minus for this, okay, so we just factor out 3. And then 1 over a, our a is 3, arctangent of u over a, our a again is 3. Okay, so this will now be the uh, uh, integral now for this. And then we will evaluate this from s to infinity. Okay, so simplifying this, now we can cancel 2 and 1/2 here. So this will just become arctangent of u over 2. And then minus, we can cancel 3 here. So this will become arctan of u over 3. Okay, so we will now evaluate this from s to infinity. Okay, so we just substitute infinity to all u here, minus, then substitute s to all the variable u here. So doing that, this will become arctangent of infinity over 2 minus arctangent of infinity over 3 minus arctangent of s over 2 minus arctangent of s over 3. Okay, so here, again, if you divide infinity by 2, okay, if you divide infinity by 2, okay, will that change? Actually, that will remain as infinity, right? Also for infinity over 3, if you divide infinity by 3, okay, that infinity will not change. Okay, it will remain as infinity. Okay, so meaning to say, if we solve for arctangent of infinity, infinity over 2 will just be infinity, and then infinity over 3 will just also be infinity. So this will just become 0. Arctangent of infinity minus arctangent of infinity, and then it will just be cancelled out. Okay, so that will just be 0. And then, actually, there's a value for arctangent of, let's say, you assume a value. Okay, arctangent of, let's say, 99999 hanggang infinity. That is pi over 2. Okay, so also for arctangent of infinity over 3, which is just infinity nga, no? So that will also be pi over 2. So pi over 2 minus pi over 2, that will just be 0. Okay, so simplifying this, no? So we just distribute negative here for this and this. Okay, so this will become arctangent of s plus 3, no? So this will now become positive, negative times negative, and then negative times positive, that will become negative arctangent of s plus s over 2. So this will now be the answer for this. The Laplace transform of the given f of t is just arctangent of s over 3 minus arctangent of s over 2. Okay, so this is just an additional problem. Okay, so find f of s if f of t is equal to t times e raised to negative 3t times cosine 5t. So as you can see, the given f of t here, okay, the general given for f of t here is 3 functions. This is a product of 3 functions, t, e raised to negative 3t, and then cosine 5t. Okay, so for this, to solve this, okay, we have to apply the theorems that we discussed. Okay, so if here, if we are going to apply, let's say, we apply, what are the topics that we discussed? Okay, if we will apply S-differentiation, okay, we need t here. Okay, so since there's a t here, we can use S-differentiation. Okay, but similarly, since there's e raised to negative 3t here, we can also apply, what do you call this? first shifting, right? So here, no, it's like you're going to, um, solve this, in a chain rule way, right? Like in your ano no derivative. So since there are three components here or three functions here, okay, combined together. So we will it's like chain rule. Okay, so let's say we solve it first using um, what do you call S differentiation. Okay, let's say we use S differentiation. So what we need there, no, to for us to be able to use that is t. Okay, so this is the S differentiation. Okay, so using S differentiation, so that will become negative 1 raised to 1 derivative of Laplace transform of f of t. So in this case, the f of t here will be e raised to negative 3t and cosine 5t. Okay, so this will be that function, that f of t. Okay, now, if you are going to solve for the Laplace transform of e raised to negative 3t cosine 5t, okay, so we will apply this. So this is first shifting theorem. So we will apply this to solve the Laplace transform of this. So applying the first shifting theorem for that, so we just solve for the Laplace transform of f of t for this, which is cosine 5t, and then replace s by s minus a, wherein s minus a here is s plus 3. Okay, so from here, let's just solve first for this, okay, for Laplace transform of cosine 5t. So the Laplace transform of cosine 5t, that is s over s squared plus 25. Okay, so we replace s by s plus 3. So that will become s plus 3 over s plus 3 squared plus 25. Okay, so from here, we are going to derive this. Okay, we will derive this. Okay, so here we have no choice. We will use a quotient rule for this, no, to derive this. So we first um, simplify the denominator, no? So s squared plus 6x s plus 34 will be the simplified form of this denominator. So using quotient rule for this, okay, again, quotient rule for differentiation, v du minus u dv over v squared. Our u here is s plus 3. Our v here is s squared plus 6s plus 34. So again, that is v du. So our v here is s squared plus 6s plus 34. And our u, so du, v du. So the derivative of our u is 1. Since the derivative of s is 1. Derivative of 3 is 0. So that will just be 1. Derivative of s plus 3 is just 1. So that will just be 1 minus u dv. Our u here is s plus 3 and then derivative of v. So that will just be 2s plus 6, right? The derivative of s squared plus 6s plus 34. So simplifying this, so again, over v squared, no? So our v is s squared plus 6s plus 34. We just squared that. Okay, so after that, so there's still a negative 1 here, okay? So after that, we just simplify this. So simplifying this, we just distributed, no? We just distributed this and this. Okay, so this will now become the result. And then after that, we combine like terms. Okay, we combine all s squared here and all s here and then all constants here. So this will now become negative s squared minus 6s plus 16 over s squared plus 6s plus 34 squared. Okay, so simplifying this further, so there's a negative here, negative 1 here if we multiply that to the numerator, of course. So that will become positive s squared plus 6s minus 16. Okay, so this will now be the answer for this. Okay, so take note here, okay, that if you can also start solving this, no, by applying first first shifting theorem, and then after that, no, you apply S differentiation. So in any order, you can do that, okay, and it should give you the same answer. So you can try to answer that using that way. Okay, you first apply first shifting, okay, and the f of t for that will be t times cosine 5t if you apply first shifting theorem, and then the Laplace transform of t times cosine 5t, you will apply this. Okay, so try to solve that if it will be if that way will be easier, no? So it's for you to judge, no, if you answer that. Okay. Okay, so that concludes our discussion. I hope that you learn and attain the learning outcome for this topic. Okay, and see to it that you subscribe to this channel and you hit the like button. Okay, so you can also share this to others, no? So why not? Okay, so also for your reward, because you listened to this discussion on time, I will give you a bonus point. Okay, so what you're going to do is just comment your name, your section, and the concept that you learn from this topic. So the first 5 students to comment will receive the bonus points. Okay, so I hope that you see this. Okay, so do not procrastinate, class. Do not procrastinate. So study what you have to study now, not later, not tomorrow, but now. Okay, so see you soon again. Bye bye. God bless. Keep safe. Bye bye.